All right, hello. Can you hear me in the back? I'm good? All right. Welcome to Data 8, Lecture 37. Today we're going to be talking about classifier evaluation, or how to choose a good classifier. Some announcements. So yesterday, Jupyter Hub was down because of the wildfire that happened near Berkeley. They actually turned off power to the entire campus yesterday. It turns out that afterward, the UCP said it didn't have to turn off power to the entire campus, so we could have had Jupyter Hub online yesterday, according to the UCPD, but unfortunately they decided to shut it down. So Jupyter Hub was down for most of yesterday afternoon plus evening. It is back up now, though. Jupyter Hub will also be down this Saturday. You should probably plan for it to be down that entire day, so the entire Saturday. Hopefully it won't be down for like the entire afternoon plus evening, but you should probably plan accordingly just in case something goes wrong. They're doing building maintenance at the building where our servers are hosted, and so Jupyter Hub is going to be down on Saturday. Because of those, Project 3 deadlines are pushed back one day. So the checkpoint for Project 3 is no longer due Friday. I was going to make it due Saturday, but then I remembered that Jupyter Hub is also going to be down Saturday. So now the checkpoint is due Sunday. The checkpoint is due Sunday, and the entire project is due Wednesday of next week. Doesn't mean you should wait until the deadline to start it, because you have to study for your final as well. Your final is on Thursday of next week, so the day after Project 3 is due. It will be from 2 to 5 p.m. We have the data labs for the rooms, and we'll be sending out seating assignments shortly. Any questions? Yes, Kevin?
The slides are not up yet. So.
The slides are not up. Well, let's see if I can fix that. All right, here we go. Let's see if I can do some magic here. Take my link. Take that. Slides. This is 37. All right, got my slides. Like 37. See if that would go. All right, so that should go up in a couple minutes. Thanks for pointing that out. OK. Oh, and I forgot to mention, next week, there will be no lab assignments. Instead, your labs are going to be kind of office hours style final review times. So you'll want to go to those if you want to get some more practice and reviewing for the final. Lectures Monday, Tuesday, and Wednesday next week are going to be final review as well. They're going to be mostly led by my TAs. And we're going to kind of go through the concepts and do some practice problems together. That also means that tomorrow's lecture is the last lecture for this class. And today is the next last lecture. So I'll see you guys tomorrow for the last lecture. Yeah, Sean?
Do we set up office hours as well?
Yeah, so office hours will be scheduled as normal. Although next week there will be no office hours on Thursday because you'll be taking your final during the office hour time.
And you said there's no lectures next week?
So there's lectures Monday, Tuesday, and Wednesday, but there'll be final reviews instead of like more content. Any other questions? Yeah, Vanessa?
Are lectures next week also count for like attendance credit?
Yeah. And the final will count for, well, technically the final goes on for 3 hours. So we'll make the final count for 3 hours of attendance credit. So you should go to like one review session to get attendance credit for that week. Although you'll probably want to go to all 3 to get the review. Yeah.
Are the labs going to be like, taking attendance?
Are labs going to be taking attendance next week? I believe not. I believe not. Yeah.
Will the lectures review material be posted online before the actual lecture?
Will the lecture review material be posted online before the actual lectures? You mean for next week?
Yeah.
So next week we'll try to. We'll try to. But who knows what will happen? It's a final. All right. If there are no more questions, let's do a quick recap of classifiers. So yesterday, Professor De Niro introduced to us the nearest neighbor classifier and implemented all of that in code in Python in a notebook yesterday. What I'm going to do is recap the high-level ideas of classification and the nearest neighbor classifier. And then we're going to talk more about how to choose a good classifier. So yesterday, we didn't talk really about choosing a good K. We're going to be talking about that today. And I'm going to show you some pretty pictures. Okay, so let's get started. So if you recall, the nearest neighbor classifier, the way it works is if we're trying to make a prediction about an example, what we do is we take that example, take its attributes, And then we look in our training set. We look at our training set and we say, okay, I think that this point, if it looks close to the points that are already in my training set, it'll probably also be classified accordingly, according to the same way my training set points are classified. So we take a look at my training set, find the closest points, find the points that are most like my training example. Once we find those points, we look at the labels and we make a prediction. So to classify a point, we take an example. We find the k nearest neighbors in our training set. So k here just means the number of neighbors that we're going to look at. Usually we'll pick an odd number. So if k is 3, we'll take my point, look at my training set, find the 3 closest looking points in my training set. Once we find those nearest neighbors, we look at the labels from our training set. So we say, OK, these were the 3 nearest neighbors. 2 of them were labeled 1. 1 of them were labeled 0. So they take a vote, and the winner is 1. So I make a classification based on that majority vote of the labels in my training set. So let me quickly run through the code that we looked at last time. All right, so here we go. Make that bigger. All right, so we were looking at this data on breast cancer. Okay, so we have here some attributes about each particular image, and we have here whether or not the cells were cancerous or not. What I'm going to do is just run through this code. So if you recall, yesterday when we plotted like 2 different attributes of this data set together, since they're all integers in my data set, we weren't really able to see, all the points got kind of stacked on each other. We made a scatter plot. So what I did here was, just like yesterday, took all the points and jittered them a little bit so you can kind of see where most of the points are falling. So it looks like we have a big clump of points here, big clump of points here. Here's kind of a mix. Okay, so we have here our data. These are 2 attributes. What we did yesterday was we defined distance. We defined distance according to the Euclidean distance, or the distance on a plane or in 3-dimensional space. And so what we did here is we said, OK, every time I get a new point, I want to find how far away each other point is to it. To do that, we need to define a distance. And here's what we did yesterday, where we can find distance between 2 rows, looking at the distance between each of the individual numbers. All right. We defined these functions yesterday. So once we compute the distances for all of our training examples, we can find the k nearest neighbors with this function called closest. Then we can use majority class to take that vote of labels. And then finally, this classify function just calls these 3 functions in order. And so we get back the classification for a particular example. So yesterday, we had this row. This is the 12th row, or the row number 12 of my patient's table. We can see that it has these attributes. And it was a cancerous cell. Okay, so these cells were cancerous, and it has these attributes. So what I'm going to do now is let's find out what my classifier would predict if I used a k nearest neighbor classifier. Okay, so grab that. All I have to do now is just call classify. Classify. Let's take my training set, so patients. I have to make sure to exclude the class column. And I'm going to take my example. And let's say 5 nearest neighbors. Let's see what we get. So our classifier says this example will be classified as 0, non-cancerous. But unfortunately, we were wrong, right? So the original data said 1. Our classifier said 0. Well, maybe we can try another example. What if we tried 20? 20. Let's see what happens now. So row 20, our classifier says 1. And we look, and indeed, it is 1. Okay, so our classifier gets some things right and some things wrong. And now we want to ask the question, OK, overall, how does our classifier do on the entire data set? Okay, so we want to be able to evaluate the effectiveness of our classifier. What we want to do is we want to say, OK, the classifier would have classified these points accordingly. So this point gets 0, this point gets 1, this point gets 0, et cetera. And the way we define accuracy is how many guesses did the classifier make correctly. That's pretty much the definition of what we do. All right, so what we do is we make our predictions using a test set. So we have our test set, make our predictions, and then we compare those predictions to the actual labels of data in our test set. if our data were sampled at random from a population, then we can infer accuracy on the population. So this is why we split up our data into training and test, because our training set was used to like kind of make our classifier. Our test set hasn't been touched. And our test set, we know if our sample was created randomly, our test set is also a random sample from a population. So we look at the accuracy for the test set, and if we find the accuracy for the test set, we can infer the accuracy for the population. So we can say, OK, the accuracy on the test set is probably close to what my classifier would have actually got if we could look at the entire population. It turns out that if you try to evaluate your classifier on the training set, you get some bad results. And I'm going to show you why. But first, let's take a look at our classifier. Okay, so we saw this yesterday. What I did here was I took the patient's table and I split it up into a training set and a test set. So when you make a train test split, what you want to do is you want to shuffle first. So I took a sample with replacement false to just shuffle my rows. And then I took the top 342 rows, and then the next 340 rows or so. Half goes in my training set, half goes in my test set. We defined this function yesterday called evaluate accuracy. Okay. And what it does is, I have a little demo here. Okay, so what it does is this. So here are my training set points. Okay, training set points here. The red dot is 1 point from my test set. So what I'm going to do is take a look at this point here and say, what would my classifier have guessed? Let's say in this case that we're using a 1 nearest neighbor classifier. So here, the red dot is my test set point. I look at the nearest neighbor, it's blue, so I'll classify this as 0. And indeed, the original class is 0. So good news. Let's try a different point on my test set. So I got here 100. 100 was originally, so here the nearest neighbor is 0, and the original class was 0. Excellent. What about 188? So here 1 and 1. OK, nice. Let's keep going. 0, 0. Okay, so basically what we want to do is you want to go through every single point in our test set, look at what our classifier would have predicted, and see if it was right. It just so happened that all of them are right so far. Let's see if I can get one that was wrong. Let's take a look. 0, 1. No, it's doing pretty well. Pretty well, 0. OK. What we can do now is ask Python to look at all the points in my test set and look at the entire accuracy. OK, so I have here this function that does that. So all I'm going to do is call it. So I'm going to call evaluate on my train set, and give it my test set. Let's say I want to find the accuracy. Let's do 1 nearest neighbor first. Now, in reality, when I'm making the classification, I'm not just looking at 2 dimensions. I'm not just looking at 2 variables here. So here, I'm only showing you 2 variables because I can't show you like a 15-dimensional plot of the points. I'm only showing you 2 variables here. So this is what we're doing here is we're saying, OK, this is what my classifier would have done if I only had 2 variables. In reality, when I call evaluate accuracy, what it does is it's looking at all my variables, all like 15 or so, and then looking at the closest points in all 15 dimensions. So I find that, wow, pretty good. So we saw this yesterday. Our classifier does pretty well. Pretty well. We got 96% accuracy with 1 nearest neighbor. And what we did yesterday was that and increase in nearest neighbors. Let's see how it does on 5 nearest neighbors. It's going to chug along. And in fact, you'll find that as you change a number k, as you change that number k, you're going to get different accuracies, right? Because your classifier will make slightly different predictions. Oh, I got exactly the same accuracy. What a coincidence. OK, let's try 9. Let's see what happens there. But normally, when you change k, you get different accuracy. So not even I know what's going to happen here because I did a random shuffle. So if I do another random shuffle, I'll probably get different accuracies, slightly different. OK, so it looks like 9 nearest neighbors was better than 1 nearest neighbor. I can increase that. So yesterday we looked at like what happens if I take k all the way up to 100. Past a certain point, the accuracy starts to drop again. So like, usually what happens is when you have like some variable k here and you're tweaking that, as you increase k, usually your accuracy will go up and then back down. Why? Because if I look at this test point here, if I look at 100 nearest neighbors, then that's pretty much like all my points here. And because of that, even if I move out to here and look at 100 nearest neighbors, you see how like it's not what I want to do is like say, okay, I want to look at the points that are closest to this point. If I go look at 100 nearest neighbors, I'm all of a sudden looking at points that are like way out here that are not really close at all. Okay, so past a certain point, you're going to get a drop in accuracy as you increase k. Okay, so it looks like 9 was better. Now, let me ask you, let's suppose that I have this as my training set data. Okay, so what I did here was I jittered the points so none of the points are on the same exact position, so you can kind of see them all. Let's suppose that we're only using these two variables to make a classification. If I take a nearest neighbor classifier, so in my notebook right now, I looked at the accuracy of my classifier on the test set. Okay, took my training set and said, okay, look at the accuracy on the test set with some nearest neighbor, k nearest neighbors. What I'm going to do now is say, okay, what is the accuracy of a 1 nearest neighbor classifier on the training set? So this is equivalent to me taking this and replacing this test set with my train set, bring that to 1. What do you think that is? Calculate it with your neighbor. And you can actually find the exact number. See if you can figure it out. I might have. I don't remember.
You're comparing the training set to the training set. I just want to shot that.
Yeah. All right. How many guys think 50%? 50%? More than or less than 50%? Let's do less than. No one thinks we'll do less than 50. What about more than 50%? 50%. Okay. What about more than 90%? All right. How many guys think 100%? You guys got me. Okay. So okay, so here's what happened, right? If I look at the accuracy of the training set with itself for 1 nearest neighbor classifier, let's say I take this blue point down here. What would I classify this blue point as? Well, I look at the nearest neighbor, which is itself, and just say, okay, this point is blue. I look at this point right here, this is yellow. I say, okay, what's the nearest neighbor with itself? It's yellow, so I got that right too. Wow, I happen to be doing really, really well, right? But it turns out that you kind of see the problem here, right? If I use a training set to select my value of k, so here I'm trying to choose a value of k that I think is best, right? So I tried 1, I tried 5, you can try 100. If I don't split up my data into a training set and a test set and just say, okay, I'm going to take all my data for training and use it to evaluate my classifier, what will you notice? You'll always pick k is equal to 1. Right? Because when k is equal to 1, the training set gets perfect accuracy on itself. So unfortunately, you don't want to use a training set to evaluate your classifier. And that kind of goes back to what I was saying here, where I want to split up my data into training and test. Because once I've trained my classifier on a training set, the accuracy on the classifier on the set will increase. It's no longer like just a new random sample from the population. I've used it to make my classifier. So it's no longer just the accuracy that my classifier would get on the population. I need some data set that hasn't been touched to evaluate the value, to evaluate my classifier. And that's why I need the test set. Did you have a question?
Yeah, the shuffle function that you wrote, what exactly did it do?
So when I take my data and I want to split it up into a training set and a test set, I want to randomly shuffle the original rows and then make the split. That's just so I can evenly distribute the rows. You kind of see what I'm saying. So if for example, in my training set, I happen to have the rows sorted by something. So if all my zeros appear on top and all my ones appear on the bottom, if I just split that, I'm not going to get a good split, a representative split. So what I want to do is I want to shuffle the rows first, just in case they had some ordering, and then I can make the split safely.
And the size of the
Yeah, so how big should my training set and test set be? So it's kind of, you get kind of have to strike a balance here. So usually what people will do is they'll try to put more points into training so that the classifier will get more accurate in the long run. So as you get more points into your training set, your classifier gets more accurate. But as you lose points in your test set, it becomes harder to evaluate your classifier. So you kind of make a trade-off there. Typically what people will do is something like 80% in training set, 20% in test set, or 90% in training and 10% in test set. But you want to make sure you have enough data in the first place so you can make those splits and still get enough data in both places. Yeah. So usually you want more in training. In this particular example in class, I just split it in half, just to kind of show you one way to split it up. But you can do pretty much anything you want. If you only leave 1 point in your training set, well, your classifier will always make the same prediction, right? If your point there is blue in your training set, your classifier will always predict blue. So you usually want some more points in there. Yeah, Sean?
And where do you get your validation set from?
Where do I get my validation set? Ah, what a great question. So I haven't talked about validation. But so typically what we'll do is we'll use our test set. So we're using our test set now to select the value of k, right? So let me go back to my demo. So first of all, let me show you what it is on itself. Again, what we're trying to do here is I'm changing the value of k, and I'm trying to ask the question, what value of k is the best? Usually we don't know what value of k is the best until we actually look at the accuracies. Here the accuracy was 100%, but it doesn't mean that k equals 1 is the best choice of k, because I can't use a training set to evaluate the accuracy of my classifier. So that's bad. So I look at this and I say, OK, it looks like 9 nearest neighbors is better than 1 nearest neighbor. So I'm using the test set to evaluate, to pick a value of k for my classifier. And what Sean mentions as the validation set is, so again, if you go back to my slides, let's go back to my slides. So again, I'm using this test set to pick k. So I'm classifying this test set over and over again and then picking the k. That means that I've touched this data. So if I touch this data, I again cannot use the accuracy here to say, OK, my classifier will get this accuracy or around this accuracy on population. I need a third set of data that's untouched. A third set of data that's untouched by my classifier at all to say, OK, this is my final accuracy. So typically what we'll do is when we split into training, test, and validation, we'll make 3 splits. So we'll split 1 to training, 1 to test, and 1 to validation, making sure that we don't allow the classifier to look at points from training set to evaluate the value of k. And we make sure that the classifier can't use the points from the validation set to get the final accuracy. Yeah.
So what is the difference between the test set and the validation set?
Yeah, so what's the difference between test set and validation? So basically what the difference here is we use a test set to choose k. We use a validation set to get the final accuracy of our classifier. Yeah.
Why can't you just bootstrap the test set?
Why can't we just bootstrap the test set to
use as a validation set instead of like getting a whole set?
Why can't we just bootstrap the test set to get a validation set? I think that's still bad because when you bootstrap a sample, the new sample looks like your original sample. So if you bootstrap the test set to use your validation, you'll still get inaccurate accuracies. Like your evaluation will still be inaccurate because your validation set will look very much like your test set. What you want is that validation set to be completely like random. Yeah, Kevin?
So basically when you bootstrap the test set, you're getting original data. So if you're using it, you're basically correct every single time. And you're getting an inaccurate accuracy because of that? Or is that what you're saying?
So if you bootstrap the test set, what's going to happen is you will get it. When you finally get your final classifier accuracy, it's going to be not accurate. Your accuracy is inaccurate. Basically, what you can do is this. You can actually try it out. So if you go here and look at my test set, you can actually just take this and bootstrap this and see what you get as your accuracy, and compare that to what you would have gotten if you had split out a validation set beforehand. You'll notice that the test set accuracy, if you bootstrap the test set, the accuracies in general will be slightly higher than if you had taken a new validation set and used that. All right, excellent questions. Are there any more? Yeah, Saeed.
Every time you call evaluate accuracy, are you like retraining it?
So every time I call evaluate accuracy, am I retraining it? Yes, in a way. So what I'm doing here is I'm saying, OK, for every point in my test set, look for the nearest points in my training set. If I had accidentally flipped the two, so if I had flipped these two guys, test set, train set. What I'm essentially doing here is I'm saying, OK, this is now the examples I'm going to use to train my classifier. And I'm going to look at the accuracy on the training set. So if I flip the two, I just put the data sets in different places. And so in a sense, yeah, we are retraining it each time I call evaluate accuracy. Yeah.
We keep manually guessing what our K is. Is there a line code that gives us the highest percent accuracy?
Yeah. So I'm kind of tired of changing this value of K over and over again. It's a great use for, say, a function. I can just write a function that calls this with different values of K, and then use a for loop to call that function over and over again, and just go through some values of K and pick the one that has the best accuracy automatically. Yeah. Mm-hmm. Can we use minimize to choose the K? In fact, you actually can. You'd want to use something you wouldn't want to minimize your accuracy. You'd probably want to maximize it instead. But you can imagine just doing like 1 minus the accuracy and then minimizing that. So what you'd want to do is you'd want to create a function here that says, OK, because minimize will choose values for you. So what happens is if you call minimize and say choose some values of K, it'll try to do that. The unfortunate problem with minimize is that it will allow values of K that are not integers and are not odd. So it'll just say, OK, so the minimize function works by just trying a bunch of different values until it finds the one that gives you the lowest number. But if you just say try a bunch of different values, what it will do by default is try like 1.5 or 2.5. And you can't look at 2.5 nearest neighbors, unfortunately. So minimize, you can, if you like tweak to minimize a bit, you can make it work. But minimize as it is will not work for choosing the value of K. Any more questions? OK. Well, I promised you some pretty pictures. I'm going to show you some pretty pictures. Talk about decision boundaries. Oh, attendance first. All right. And go for it. Here it is. It's not open yet. Oh my goodness. My water bottle. OK. Did I? Oh no. Oh, you're right. OK, now it's open. All right, so let me show you something kind of cool. So what I'm going to do now is take a look at some data that we've seen a couple days ago. This is data on chronic kidney disease. And we had the blood test results of some people, okay, some patients. We had the blood pressure, specific gravity, all this stuff. And at the very end, we had whether or not they had chronic kidney disease or not. Okay. So we have here a bunch of attributes, pretty similar to our nearest neighbor problem. So what we can do is I can say, okay, here are two of my attributes. If I just use these two attributes to make a nearest neighbor classifier, what would I categorize this point? Right here. So what I'm going to draw is the same scatter plot here. I'm going to draw this point and see what the nearest neighbor is. So here I have a function that draws the closest point, and we get the nearest neighbor to this point was this yellow point over here. Kind of weird, right? What happened? Talk to your neighbor about it. I wrote my function correctly, but this is indeed a nearest neighbor. Why? All right, so what happened? The x-axis, the axes, right? The units on the axes are different. This right here is in like 10 to 12, 12 to 15. This goes from 200 to 300. So a little change so if I go up one box on the y-axis, this is really, really big compared to how much change is in the x-axis. So what we see here is that even though these points look really close on a scatter plot, because the units here are so big, this point is actually the closest one. How can I fix this? Well, what I want to do is I want to convert to standard units, right? Only in standard units can I directly compare two variables that have different units. I'm standardizing the units. So what I'm going to do now is, now we can see, okay, the point here is indeed, this point is indeed closest to this one when I convert to standard units. Okay. So look at this point here, which is red. I'm going to move that point down, okay? Move that point down. So right now, if I use a one nearest neighbor classifier to predict that red point, I would predict yellow. So I'm going to move it down. I'm going to draw the closest point each time. So I'm moving it down. And nearest neighbor is now, let's keep moving, there. Okay, so as I move it down, the nearest neighbor changes. If I keep moving it down, eventually it will become blue, because now the nearest point is blue. So you notice now here is yellow. Here it was blue. So there are points at which my classifier will switch its decision, right? So it'll say, okay, if you're above this, you're yellow. If you're below this, you're blue. And what we call that boundary, that switching boundary, is a decision boundary, because my classifier will switch its decision. Okay. So as we saw, if I change my attributes, my classifier will also make different predictions. If I look at the points where my classifier switches between one class and another class, we call those points a decision boundary. It's like the boundary where my classifier switches its decisions. So what I'm going to do now is visualize that decision boundary. So here we saw just one point and where it switched. But you can imagine me taking another red point over here and moving it this way on the x-axis, right? I can take a bunch of points and move them around and see where the decision boundary is. There's an easy way to do that. So I have here a function that will draw that for me. So I have here a decision boundary for one nearest neighbor. Why do you take so long? There it is. OK. So I have here the same hemoglobin glucose plot. And what I'm doing there is I'm just saying, OK, take a bunch of points on the x-axis and the y-axis and just classify all of them. When we classify all of them like that, we can see where my classifier would have switched its decisions, right? So right here, if you had a point anywhere in this yellow region, the classifier would have said this point is yellow. If you just go over here, now the classifier says all these points here will be blue. So any new point that I see, you can kind of see from this boundary what my classifier would say about that point. So here yellow, here blue. This is a one nearest neighbor classifier. It's that nearest neighbor. So if I go from one nearest neighbor to three nearest neighbors, what do you think will happen? Talk to your neighbor about it. All right, well, let's try it out and see what happens. So 1 to 3. That's taking an awfully long time. Oh, I think I know why. Oh, okay. So what I'm going to do is, okay, so it looks like these take a long time to kind of scroll around. What I'm going to do is I'm just going to take this and go from 1 to 3 to 5 to 7. So it'll kind of like chug along and do some computation. Okay, so here's 3. Do you remember what it looked like when it was 1 nearest neighbor? So this is now all blue. Before, we had a yellow kind of curve. So if you saw before, we had a yellow curve like in this area right here, right? This part right here is all yellow because the yellow point here, there's like one yellow point here, and so the nearest neighbor to that yellow point is like all of these points here. There is a little, unfortunately, it's like chugging along, so I can't show you, I can't go back and forth like I wanted to. I'll probably do it after it loads everything. But if you remember before, there was like a little like kind of little like chink right here. It went this way sharply and then down this way sharply. And the reason why I did that is because, again, if you're looking at one nearest neighbor, right here's a yellow point, right here's a blue point. So the decision boundary would go in between the yellow and the blue point and then come out again. And if you notice, since we're looking at 3 nearest neighbors, this boundary is more smooth, right? Because this yellow point is by itself and it's close to 2 other blue points. So now that boundary will include a yellow point and just go like that. So it's smoother than it was before. And indeed, if let's see what's happening. It's still going. OK, so indeed, if I go from 1 to 3 and then 3 to 5 and then 5 to 7, what you'll notice is that this decision boundary will get smoother and smoother. Oh my goodness, it just broke. Connecting to kernel. Oh my gosh. This is problematic. OK, wait. Let's see what happens. Oh my. Can I even do 1 plus 1 now? Yes, here it is. 1 plus 1 is star. Great. OK, well, I tried to make Python do too much, and it died on me. OK, let's see if I can restart and run all. Now I feel your pain, don't I? OK, well, is it actually running anything? I'm so sad. Let's try refreshing. OK, if this doesn't work, I'm just going to talk through what happened. Oh my gosh, I have like 3. Oh my goodness. Now I really feel your pain, don't I? OK, let me ask for help. This is the chat channel that I use to communicate with the people in charge of Jupyter Hub.
Cut Jupyter Hub some slack, I guess.
Hello, UV. I'm in lecture now. And Jupyter Hub broke.
Tell them that the class says hi.
Also, the class says hi. Also, this is live streaming. OK, we'll turn it off. Maybe what I can do is I can show you what this looks like on my computer. Okay, let me see if I have it up. In my notes. All right. So indeed, you can actually set up Jupyter on your computer, believe it or not. And you won't learn how to do so in this class, but we'll probably post up instructions on how to do that afterward. OK, so let's see what happens. I have this on my computer. Now, run that. Oh, yes, we got it. All right, we're back in business. All right, run that. Here we go. You can actually set it up on your own computer, and then you don't have to worry about Jupyter Hub problems. Learn how to do that in Data 100 as well, if you're planning to take that. Okay, so here we go. OK, so where are we? OK, so 1. Yes. OK, 1, 3 to 5, 5 to 7. Get smoother and smoother, because we consider more neighbors. As we consider more neighbors, that boundary will kind of smooth out. It'll kind of smooth out, so that because we're considering more neighbors, so we get less like random variations. Let's take a look at this one in particular. So here's one. You notice here that you get a bunch of splotches, right? get some wiggliness here, splotches of blue here. Because we're looking at the nearest neighbor, there's like one blue point in this mess of yellow points here. So we get these 2 points that are classified as blue. Okay, this is not super good because any little blue point that happens to be there will affect our classification by a lot. I'm going to go from 1 to 3. Okay, so you notice less splotches. In particular, this one is gone because we're looking at 3 nearest neighbors. This one's kind of gone, right? This one's still here because we had a couple of blue points here. So let's keep going. As we increase k, our decision boundary will change. Eventually, it'll get smooth. But as we increase k, if we increase this k to 100, let me just see what happens if I do that. Will this work? I've never tried this. 101. All right. Okay. Okay, let me try it. Decision boundary. And I'm going to say jittered. And 101. Let's see what happens now. This is probably going to take a while. That's to classify every single one of these points here. OK. But as I increase k, you'll notice that my decision boundary tends to get smoother. If I take k to some really big number, what do you think will happen? Actually, why don't you talk about it? What do you think will happen as this is running? Go ahead and talk with your neighbor about what will happen.
Well, it increases that if you go to like k equals to 107, that's what I was talking about.
All right, well, it's done now. Let's take a look. This is so suspenseful. Let's take a look. Whoa, what do we see? So as we increase k, right, if you look at 101 nearest neighbors, when you're like in this area right here, you're looking at all these blue points plus a bunch of these yellow points. And so this decision boundary is super, super smooth. In fact, maybe a little bit too smooth, right? A little bit too smooth, because what about these yellow points here? I would probably say that a point that lands in this region here should probably be yellow. But if k is 101, then we're looking at all these blue points here and a couple of these yellow points. So we say this region right here is blue. So you can see that there's some trade-off here between looking at nearest neighbors, looking at the number of nearest neighbors, keeping it small, you get more detail, and making it large, you get the smoother boundary. Okay. So typically, you won't know. When you actually make a classifier, you won't really know what value of k is best. Again, what you want to do is you'll want to just go up and just try out a bunch of values of k. You saw how long that took me right now. So basically, what you'll do is you'll try out as many values as you have time to try out. And if I scroll all the way up, so you pick your accuracy and just pick the one that gives you the best accuracy. And that's how you choose a value of k. As you change the value of k, your decision boundaries will also change. And ideally, you choose a value of k that gives you a decision boundary that's not too wobbly like this one. Ideally, you don't really want those splotches there unless you actually think that there's a pattern there in the original data. But you don't want something that's super smooth either. And hopefully, your choice of the value of k will reflect that in your decision boundary. OK, so let's recap. Oh, darn it. Yeah, go ahead.
Why do you not want it so smooth? Why does over smoothing represent error?
Yeah, so why is making it super smooth bad? Well, it's because if you look in this, let's say we take a look at this clump right here. This clump right here is all yellow. And because this clump is all yellow, it makes sense that if I got a new point and it happened to have 0.2 bland chromatin and 0 single epithelial cell size, if I got a point that actually landed right there in the middle of that clump, I would probably want to say that point is yellow. It makes sense that because it looks like this right here is a yellow region to my eye, and so I probably want to say at that point, same for this clump right here, it's all yellow here, and I'm saying these are all blue. So if my decision boundary considers too many nearest neighbors, I'm going to look at points that are really far away from my data. So the reason why this is all blue here is because of this gigantic mass of blue points right here. When I look at all these blue points, it looks like my decision boundary is like this. I'm looking at all the blue points here, even though I have closer yellow points, I can just make a decision. Yeah. Any other questions? Sorry, I didn't ask for questions. All right, so let's recap. So these are supposed to appear one at a time. They didn't. Here we go. So k nearest neighbor classifier. Look at the k nearest points, take a vote, make a classification. How do you choose k? You look at the accuracy of your classifier on the test set. So not your training set. You want to make sure to use your test set. The decision boundary shows us where the classifier made it, change its prediction from 0 to 1 or 1 to 2 if you have more classes. And it changes based on your value of k. In particular, k small means your decision boundary will have more detail. K large means that your decision boundary will be smoother. That's all I got for today. I'll see you guys tomorrow.